Hi everyone. Thank you very much for joining the presentation today. The topic I'm going to talk about is the NAND flash architecture combines QLC density with SLC speed. This architecture is called XNAND, which means Express NAND. My name is Andy Xu. I'm the founder and CEO of Neo Semiconductor. We are a startup company based in San Jose, California since 2012. NAND flash memory is migrating from TLC toward QLC. But for each generation, when the density becomes bigger, the price getting cheaper, and the performance also becomes slower. From TLC to QLC, the sales VT levels are increased from 8 to 16. This greatly increases the read time and write time, especially for write. Such slow write speed prevents QLC from being used in many applications that require heavy write workload. In order to increase the write speed, SLC cache is widely used. It postpones the QLC write until the system becomes idle. However, for write-heavy workload such as data center or NAS, the system may not have enough idle time to move the data from SLC to QLC. Once the SLC cache is full, the data will be directly written to the QLC cells. This will cause the write speed drops to about 10%. So how to increase QLC rewrite speed? The simple answer is to increase the number of planes. More planes will allow more pages to perform read and write operation at the same time. This increases the rewrite throughput. It also reduces the binary length as well as the capacitance. This reduces the binary delay in read and program verify operations. Please notice, the planes we are talking about here is the planes in binary direction. For the planes in word direction, since they cannot increase the rewrite throughput. For the plane in word direction, since they cannot increase the rewrite throughput, we are going to ignore them here. However, this solution comes with high price. Because each plane needs 16 KB page buffer to perform read and write operation. Increasing the number of planes will significantly increase the number of page buffers. For 4 planes, the die size is increased by 30%. For 16 planes, the die size will be increased to about 3 times. Because for conventional NAND architecture, one page buffer is connected to one B9. Each plane will require 16 KB page buffers to connect to the 16 KB B9s. So, how can we increase the number of the planes without increasing the number of page buffers? This slide shows the basic structure of XNAND. XNAND connects one page buffer to 16 or more B9s. The page buffer can perform read and write operations to the 16 B9 in parallel. This reduces the number of the page buffers in each plane to 1/16. Therefore, the plane number can be increased to 16 without increasing the die size. Compared with the conventional NAND architecture using 16 planes, XNAND's die size is only 1/3. By using XNAND architecture, the number of the planes in binary direction can be increased to 16. So the rewrite throughput can be increased by 16 times. The binary delay is also reduced to 1/16. So XNAND architecture can increase the rewrite speed greatly without increasing the die size. This slide shows the performance estimation for QLC XNAND. By reducing the binary capacitance, the read time can be reduced to 30%. The program time can be reduced to about 40%. And the read throughput can be increased by 27 times. The write throughput can be increased by 14 times. This slide shows a diagram for the performance comparison. You can see XNAND's speed is much higher than the conventional NAND due to its 16 planes. This slide shows the performance comparison between NAND and XNAND. You can see the performance of XNAND's QRC is similar or higher than the conventional NAND's SLC, except the random write speed. This slide shows the comparison between conventional QLC, SLC, and XNAND. XNAND can achieve outstanding performance with only 25% die cost of SLC. This slide shows a random read speed comparison between NAND and XNAND from SLC to PLC. As you can see, XNAND's speed is 3.5 times faster than conventional NAND. For random write speed, XNAND is 3 times faster than the conventional NAND. For sequential read, XNAND provides about 30 times speed of conventional NAND, and 15 times sequential write speed of the conventional NAND. This slide summarizes the comparison from SLC to QLC. You can see XNAND's performance is much higher than the conventional NAND. It can achieve 3 times random read-write speed and 15 to 30 times sequential read-write speed. This is amazing, isn't it? For the challenges, how do we perform QLC rewrite operation to 16 bits with only 1 page buffer? To achieve this goal, we developed 6 design solutions for XNAND architecture. The following section will be technical section. Since we have many non-engineer audience, I will only show you the basic concept of the solutions. We have a separated discussion section after this presentation. If you are interested, please join us for more detailed discussion. The first solution is called multiple binary write. A page buffer will load 16 data into 16 bits. The data will be held by the binary capacitance and programmed to 16 cells in parallel. Binary sharding can be used to eliminate the binary coupling. But binary sharding will reduce the program throughput by 1/2. So we develop a dual binary loading sequence to eliminate the binary coupling. This allows all binary to be programmed together to double the write throughput. This slide shows the data loading sequence from the I/O bus to the page buffers and then to the binary. You can see the loading time from the page buffers to the binaries is 1 microsecond per plane. So it has plenty of time to load data into a binary capacitance. The second solution is called multiple plane QRC program. The 16 planes are divided into 3 groups. Each group contains 5 planes. The input data D0 to D3 are stored in the 4 planes and then programmed to 1 plane. During program verification, the cells are read and compared with the input data stored in the 4 planes. This architecture increases the program throughput by 3 times. To further increase the program throughput, we developed another architecture. This architecture divides 16 planes into 5 groups. Each group contains 3 planes. 1 for programming, 1 store the input data, and 1 store the data read from the cells. By using this architecture, the program throughput can be increased to 5 times. This slide shows the data input and program sequence for the QLC programming. The data of multiple groups are sequentially input and then programmed together. This increases the program throughput and also eliminates the requirement of the multiple core state machine. One important operation for QLC programming is the program suspend read. Because the QLC program time is very long, when the system requests the data, the program operation will be suspended to read the data first, and then the program operation can be resumed. This architecture allows the input data to transfer from one plane to another, so the system can read data from the plane that stores the input data. The first solution for XNAND is called multiple binary read. We use current sensing for QLC. Each binary has a pull-up device to apply the loading current to set the binary voltage. The binary with on cell will be pulled low by the cell current. The binary with off cell will be pulled high by the loading current. Then the binary select gates are sequentially turned on to let the page buffer to sense each binary's current. By using this way, the 16 binary can be read simultaneously by using one page buffer. In another architecture using half binary read, the binaries are divided into even and odd. The probe device can apply the loading current to all the even binaries for read, and apply the shielding voltage to all the odd binaries for shielding. So the probe device and the shielding device are combined. This results in high-speed, reliable current sensing without adding extra device. This slide shows the conventional read operation of the QLC cell. The cell is read by 4 forward voltage to get 4 data. And then the control logic will compare the 4 data to generate the final 1-bit data. This operation requires 4 data latches to read just 1-bit data. So by using this conventional read scheme, the 16 planes will be divided into 3 groups. Each group contains 5 planes. The data read by the forward voltages will be stored in 4 planes and then converted into 1-bit data in another plane. This architecture increased the read throughput by 3 times. To further increase the read throughput, we developed a new QLC read operation called the single latch read. The cell is read by forward voltage and keep on flipping the read data to get the final data. Therefore, you only require 1 data latch to read the QLC cell. By using this way, it only needs 1 plane to store the read data. Therefore, the read throughput can be increased by 8 times. The 6th solution for XNAND is called SLC QRC Parallel Programming. This unique operation allows the data to be programmed into QLC in SLC speed. The array is divided into 3 banks, one for SLC program, one for QLC program, and the other one for erase operation. The data is alternately programmed into SLC page in bank 1 and bank 2. When the data is programmed to one bank, the other bank will perform QLC program to move data from SLC to QLC pages. By using this way, the data can be continuously programmed to SLC page and then move to QLC pages in SLC speed. This solution solves the SLC CH4 problem of the conventional NAND. This slide shows a detailed operation for the parallel programming. When bank 1 performs SLC program to 8 planes in serial, bank 2 will perform the QLC program to 8 planes in parallel. Although the QLC program time is 8 times of SLC, since bank 2 programmed 8 planes in parallel, the program throughput of bank 1 and bank 2 will be the same. In this way, the data can be continuously programmed to SLC and then move to QLC in SLC speed. By using this SLC QRC Parallel Programming, the SLC CH4 problem is eliminated. So XNAND can be programmed in SLC speed for entire array capacity. This is very important for heavy write applications such as data center or NAS. Is it safe to store program data in binary capacitance? Yes, absolutely. Because NAND flash's binary capacitance is very large. For 16 planes, the binary capacitance is about 250 femtofarad, which is 10 times of DRAM capacitor and 50 times of NAND string capacitance. As a NAND string can hold boosted voltage for entire program path, the much larger binary capacitance can definitely hold the data without any problem. This diagram shows the program condition. In order to leak current from the inhibited NAND string, the binary voltage needs to be dropped about 0.7 volt. Assuming the binary leakage current is 5 nanoamp, it will take 350 microseconds, which is 35 times longer than the 10 microsecond program path. Therefore, the program data can be safely stored in the binary without any concern. This slide shows the condition of the data stored in the data binaries. The binary voltage needs to be dropped from VDD to below VT to cause read error. Assuming the binary leakage current is 5 nanoamp, the discharging time will be more than 1 millisecond. Therefore, it's very safe to store the data in the binaries for entire read and program operations. Besides, during read and program read-write operations, the data read from the binary to the page buffers can be loaded back to the binary to refresh the data. Therefore, the binary will be automatically refreshed without the extra refresh operation. Unlike DRAM, this refresh operation is non-destructive. It only supplies the loss charge over the binary. Therefore, the power consumption is very low. We have shown the high-speed advantages of the XNAND. However, for some applications, we may not need such high speed. Then we can go with the cost-saving option. As shown in this diagram, we can choose 2 planes, 4 planes, or 8 planes. Because XNAND's page buffer size is only 1/16 of a conventional, it can reduce the die size from 25% to 33%. This slide shows the performance of XNAND using different number of the planes. This slide shows the diagram. By using 16 planes, XNAND can achieve about 30 times of sequential read speed and 15 times of sequential write speed. By using 32 planes, XNAND can achieve about 60 times of sequential read speed and 30 times of sequential write speed. Please notice, when using 32 planes, we can connect 32 binaries to one page buffer. Therefore, the die size will not be increased. This slide shows a layout comparison of the conventional NAND, low latency NAND, CUA NAND, and XNAND. XNAND can be implemented in both CUA and non-CUA technologies. It can be implemented in 2D or 3D NAND or even serial NAND. As you can see, compared with other architecture, XNAND array can be increased to 16 planes without increasing the die size. This slide shows the power consumption comparison between NAND and XNAND. By reducing the binary capacitance to 1/16, the binary power consumption is also reduced to 1/16. So XNAND does not only increase the read and write speed, it also reduces the power consumption greatly. This slide shows a comparison of the reliability for XNAND and the other solution using binary select gates. The other solution only selects one binary for read and write operation. Therefore, all the other unselected binary will suffer from the high voltage disturb. Because you need to repeatedly read and write 6 times for 16 binary, the disturbance for each cell is increased by 16 times. This may cause reliability issue. It also increased the power consumption by 16 times. With contrast, XNAND read and write 16 binary together, so the disturbance problem is eliminated. Now we are going to talk about the applications for XNAND. This slide shows the comparison of the parallelism between NAND and XNAND. XNAND's single chip has 16 planes, so you can provide the same parallelism of 4 to 8 conventional NAND chips. This provides huge advantage for small form factor systems like M.2 or eMMC. For large systems like 2.5-inch solid-state drive, the system can have 8 to 16 NAND flash packages. So you can connect multiple channels to the NAND packages to increase the parallelism. But for small form factors such as M.2 or eMMC, it only has 1 or 2 packages. Therefore, the parallelism is very limited. With XNAND's 16-plane architecture, M.2 and eMMC can achieve the same or even higher parallelism as a large solid-state drive system. XNAND's architecture can be also applied to SLC. When applied to SLC, it can achieve the highest performance of 3D NAND. This slide shows the performance estimation for SLC XNAND. Please notice, for read operation, SLC does not require additional plane to store the read data. So its read throughput can be increased to more than 50 times. This slide shows the performance estimation for SLC XNAND for 16 to 64 planes. By using 64 planes, XNAND can achieve astonishing read throughput of almost 200 GB per second. This, of course, oversaturates the I/O bandwidth. But it opens the door for XNAND to the future high bandwidth applications, such as 3D chip integration. 3D chip integration using thousands of TSV to increase I/O bandwidth to 200 GB per second. However, the conventional NAND flash read throughput is lower than 10 GB per second. So the NAND speed will become the bottleneck if we put NAND flash into 3D chip integration. XNAND architecture in SLC can achieve 200 GB per second read throughput. So this removes the bottleneck and allows XNAND to be integrated into 3D chips. However, please notice this application will subject to the endurance cycle of SLC NAND. From Western Digital's study in 2019, It will take 5 more years for QLC to reach 50% market share. Many studies also suggest QLC will not replace TLC in many fields because of the lower performance. However, with XNAND architecture, QLC's performance can be better than today's TLC performance. This will speed up the rise of QLC NAND. So what's XNAND? XNAND is QLC density plus SLC speed. XNAND marks the coming of the age of high-speed 3D NAND flash memory. For process requirement, XNAND can be implemented by any existing NAND process. It does not require any cell, array, process, or technology change. It does not increase the manufacturing cost, and it does not require long development time for process change. XNAND is a pure design solution. The basic rewrite circuit, the page buffers, and the high voltage circuits are all remain the same as the conventional NAND. So it can be quickly implemented and build samples by every NAND flash manufacturers. We are currently looking for development partners. We are open for all kinds of business model discussion. If your company is interested, please feel free to contact us. So, what is XNAND? XNAND is a door to a better future. Thank you very much for joining today's meeting. I hope everyone enjoyed the presentation. If you have any questions or comments, please welcome to our next discussion session. You can also find our contact information in our website, neosemic.com. Thank you so much and have a great day.